Hello everyone, welcome back to the channel. I hope you're all doing great. In our previous videos, we understood what linear regression is and how multiple linear regression works. Today, we'll move one step ahead and discuss one of the most important topics in econometrics and regression analysis: the assumptions of the classical linear regression model, also known as CLRM. Before we begin, let's do a quick recap. The classical linear regression model explains the relationship between a dependent variable and one or more independent variables using a linear equation. It forms the foundation of ordinary least squares, or OLS regression, which is one of the most widely used statistical techniques. Now the question is, why are these assumptions so important? The answer is simple. These assumptions ensure that our regression model gives unbiased, efficient, and reliable estimates. If any of these assumptions are violated, the results of the model can become misleading, and our conclusions may not be trustworthy. From an interview perspective, this topic is extremely important. In many interviews, you may simply be asked, "What are the assumptions of the classical linear regression model?" Sometimes interviewers may ask you to explain just one assumption in detail. So make sure you understand not only the names of these assumptions but also their meaning and importance. With that, let's begin. The first assumption is that the regression model should be linear in parameters. Many students misunderstand this assumption. It does not mean the variables themselves have to be linear. Instead, it means that the unknown coefficients, or parameters, must appear linearly in the equation. For example, the independent variable may be squared, cubed, or transformed using logarithms, but the coefficients should still remain linear. This assumption is important because ordinary least squares can estimate models only when they are linear in parameters. If the parameters themselves appear in a nonlinear way, OLS cannot be directly applied. So always remember this interview point: the model has to be linear in parameters, not necessarily in variables. Now let's move to the second assumption. The observations should come from random sampling, and the error term should be random with an expected value of 0. In simple words, every observation should have an equal chance of being selected, and the errors should occur purely due to random factors instead of following any systematic pattern. When the average value of the error term is 0, positive and negative errors cancel each other out over time. This prevents bias and ensures that the regression line represents the true average relationship between the variables. Random sampling also helps us make valid statistical conclusions about the entire population based on our sample. Next comes the third assumption, which is the zero mean of the disturbance term. This assumption says that the expected value of the error term is 0. What does that mean in practical terms? It simply means that on average, our model neither consistently overestimates nor consistently underestimates the dependent variable. Any prediction errors are random rather than systematic. This assumption ensures that the regression coefficients remain unbiased and that the regression line correctly captures the average relationship between x and y. Now let's move to the fourth assumption, which is homoscedasticity, or constant variance of the error term. This means that the spread of the error terms should remain the same for all observations, regardless of the value of the independent variable. Imagine plotting all the residuals. If they maintain roughly the same spread throughout, the assumption is satisfied. Why is this important? Because constant variance makes OLS estimators efficient and ensures that standard errors, confidence intervals, and hypothesis tests remain valid. If this assumption is violated, the coefficients may still be unbiased, but the statistical tests can become unreliable. Now let's discuss the fifth assumption, which is no autocorrelation between disturbances. This assumption says that the error term of one observation should not be related to the error term of another observation. In other words, knowing the error in one observation should tell us nothing about the error in another observation. This assumption is especially important for time series data because errors from one time period can sometimes influence the next. If autocorrelation exists, the regression coefficients may still remain unbiased, but they become inefficient, and statistical inference becomes unreliable. So in interviews, remember this simple definition: no autocorrelation means the residuals are independent of each other. Next is the sixth assumption. The number of observations should always be greater than the number of parameters that need to be estimated. Simply put, we should have enough data points compared to the number of variables in the model. If we try to estimate too many parameters with too little data, the model cannot uniquely estimate all coefficients. For example, if we have only 25 observations but 30 explanatory variables, reliable estimation is not possible. Having more observations reduces overfitting, improves reliability, and allows OLS to produce stable coefficient estimates. Finally, let's move to the seventh and last assumption, which is the normality of the disturbance term. This assumption states that the error terms should follow a normal distribution with a mean of 0 and constant variance. If we plot the errors, they should form a bell-shaped curve where most errors are close to 0 and large errors occur only rarely. Now here's an important interview point. OLS estimation itself does not require normality. Then why do we need this assumption? Because normality becomes essential when we perform statistical inference, especially for small samples. It allows us to conduct t-tests, f-tests, construct confidence intervals, and perform hypothesis testing correctly. For large datasets, this assumption becomes less important because of the central limit theorem. And with that, we've completed all 7 assumptions of the classical linear regression model. Let's quickly revise them once again. First, the model should be linear in parameters. Second, observations should come from random sampling, and the error term should be random. Third, the expected value of the error term should be 0. Fourth, the error terms should have constant variance, also called homoscedasticity. Fifth, there should be no autocorrelation between the error terms. Sixth, the number of observations should be greater than the number of parameters. And seventh, the disturbance terms should follow a normal distribution for valid statistical inference. If you can confidently explain these 7 assumptions along with their practical meaning and importance, you'll be well prepared for interviews, university exams, and real-world econometrics applications. Thank you so much for watching this video. I truly hope this session helped you understand the assumptions of the classical linear regression model in a simple and practical way. If you found this video useful, please like the video, share it with your friends and classmates, and subscribe to the channel for more content on statistics, econometrics, data analytics, Excel, SQL, Power BI, and interview preparation. Also, let me know in the comments which topic you'd like me to cover next. Until then, keep learning, keep growing, and I'll see you in the next video. Thank you, and have a wonderful day.